Okay, today we are talking about collision theory, and we're also going to talk about reaction mechanisms. So, uh, collision theory. The essence of this says that in any reaction, bonds will be broken and bonds will be formed. Now, of course, this should make sense because you know that during a chemical reaction, you start with two reactants, you get products. The products, of course, are different than the reactants. So the only way for that to happen is if you break some bonds and form some new ones. So this makes sense. But the focus here in collision theory is on the collision, if they collide, right? So the reaction rate is proportional to the rate of, and I want to stress this, effective collisions. Because things can bounce off of each other. It doesn't necessarily mean anything happens if they do. Right? You could take 100 shots at a basketball hoop, and just because they hit the rim doesn't mean anything. They've got to go in. Well, with reactions, the collisions, not all of them result in a chemical reaction. So there are two primary factors related to collision theory. The first is what we call molecular orientation. All right, so let's say, for example, generically we have this reaction here. Okay. So I've got some diatomic molecule A2 reacting with some diatomic molecule B2. And the product is to be a compound AB. So when this reaction happens, A, here's the molecule of A, will have to collide with B in such a way where they actually make contact. Right? So here and here and here and here. So it's here, right? The collision. At this point, the old bonds are broken, but we also get new bonds forming. Now, the only way this can happen is if the molecules are oriented in the correct direction. If the A actually comes into contact with B, if they are aligned, right? So molecular orientation or molecular alignment, right, is very important. And then if they are aligned properly, then there's a chance that you could actually get your product. So first and foremost, you have to have the proper orientation. Here's an example of improper orientation, right? Let's say that you have the A molecules collide with the B molecules in this manner. Well, while this might be aligned for one of the A molecules or one of the A atoms to react with one of the B atoms, you're not actually going to get the breaking of the covalent bond within each of the molecules. So this will be unsuccessful, or it's improper orientation. Okay, so alignment is important. The second factor is the kinetic energy. There's a certain amount of energy that is necessary to make the reaction occur, and this is called activation energy, or EA, energy of activation. So, if we were to look at an energy profile, oh, actually it says here, see Boltzmann diagram. I guess we should draw in a Boltzmann diagram here. Find some space where you can. So remember, the Boltzmann diagram shows the number of particles versus the kinetic energy. And so in any distribution, there's going to be the minimum energy needed. So that red line represents the energy that is required for a successful reaction. By looking at this picture here, the vast majority do not have enough energy for a successful reaction. Only the portion past the line that's under the curve. All right, only a small proportion has met the activation energy requirement. So essentially, you have to have both factors met. You have to have the proper alignment, and you have to be one of the molecules that has enough energy. Right? So so that means the total number of collisions that occur, there's a small percentage of them that are actually effective. Okay? So that's important to understand. Not just because there's a collision doesn't mean a reaction is going to happen. The molecules might be moving too slowly. If they're moving too slowly, that's not enough kinetic energy to break the old bonds. All right? Okay. So if we look at an energy profile for an exothermic reaction, so reaction profile is not the same as Boltzmann diagram. Generically, on the x-axis, we just say reaction progress. It's not literally time because the actual measured time is not the point of a diagram like this. It's just to show you essentially before and after states. So for an exothermic reaction, an energy profile would look something like this, right? Whereas this point here represents the energy of the reactants. This represents the energy of the products. So we say exothermic because, as you know, in an exothermic reaction, there is a net loss, right? So we have a negative. And by the way, since we're on here, this could either be energy or enthalpy, right? It's the same point either way. So the delta E or the delta H in this case is negative. There's a loss of energy during the course of the reaction. Now this energy difference from where the energy of the reactant starts and when it gets to the peak here, this is the EA. That's the amount of energy needed to get the reaction to happen. So every reaction profile should have an indication of how much activation energy is needed. Right? So generically, they will all kind of look the same. Here's another example. You could have a reaction that looks something like this. Right? In the second reaction, that's got a much larger activation energy requirement. Reactions with very high activation energy values are they don't happen very, very easily. They require lots of energy, lots of effort to get the reaction going. Right? So qualitatively and quantitatively, you can judge a reaction, how difficult it is to take place by the amount of activation energy needed. Okay, and again, this one here is also exothermic, right? Because you still end up with a lower energy afterwards than before. All right, let's look at an endothermic reaction. Yikes, didn't want to do that. Okay, so you could look your reaction could be something like this. Your reactants, your products. Here we have a net gain, right? Delta E is positive, endothermic. And you can still gauge the activation energy, the same method, difference between your reactant energy and the peak. All right, so be able to interpret these energy profiles for either an endothermic reaction or an exothermic reaction. Be able to label the parts, understand where the activation energy is, how to determine it, how to determine the delta H or delta E, whichever term they're using. Okay? All right, so the second theory is what we call transition state theory. Now, transition state theory is not a competitor to collision theory. It's more of like a parallel theory, right? So it kind of enhances the two of these theories together, kind of help to make more sense of what happens during chemical reactions. So in transition state theory, it says that during a collision, there's a transition state that exists. Actually, scratch this word out. That's not placed in the right place. There's a transition state where bonds are partially formed and broken, right? And that term is called an activated complex. So, before I look at this particular diagram, let's go back to the example that we used earlier. Okay, so here, when this reaction took place, when A2 collided with B2, this right here, this whole thing would be called the transition state, right? And so what I mean by that is very temporarily, you've got a molecule that's got tenuous bonds that are both broken and formed simultaneously. And it is in between the reactant and product state. The bonds are breaking and forming simultaneously at the same time. Now, this is not stable. This does not last very long, right? Consider a relay race. Right? You guys know that in a relay, when the first runner hands off the baton to the second runner, there's a split moment of time where both runners are holding the baton. Right? That would be like the in-between. Right? So that would be like the transition state. Okay? So it happens, it's fleeting, and then immediately after this, the result is the product. So it goes from this to this, to this. Or I guess that was kind of clear from the picture anyways. Okay, so the transition state. Temporary state. Bonds are partially formed and broken, and that transition state is also called an activated complex. It's just like another name for it. So the transition state on an energy profile occurs at the peak of the hill. At the very peak of the hill, remember what we talked about high energy being unstable? Well, the peak is the least stable place on an energy profile. And so that transition state is very, very temporary because it's the most unstable. It just can't stay that way. It's very fleeting. So be able to identify where that is on an energy profile. Okay? This is a better picture here. So in this reaction, we're actually going to get the nitrogen and the carbon reorganizing itself within the molecule. And the activated complex at the peak of the hill is when your reactant is halfway in between the reactant and the product. Right? It's halfway on its way to becoming product. Here's the product, here's the reactant. This is the least stable state. Right? The amount of energy needed to get this reaction going, you have to get to that potential energy. Right? So there has to be some input of energy. And the result is that we have less energy than we started, so this is an exothermic reaction. Okay. You guys okay with that? Energy profiles, transition states, enthalpy, activation energy. Okay. All right. So back to the Boltzmann diagram. So in general, increases in temperature increases the rate. And you got this from the lab, right? In the case where you decrease the temperature, the rate decreased, well, the converse is true. If you warmed it up, it would have been faster, right? Now, this is kind of a loose rule of thumb, is that approximately every 10 degrees increase approximately doubles the rate, but this is not exactly like double. It's just kind of like, you know, it's exactly that. It's an approximation. So that means when your temperature goes from 10 degrees Celsius to 20 degrees Celsius, you should expect the rate to double. Now, Celsius or Kelvin doesn't matter because the increment is the same, right? If your temperature goes from 10 to 30 degrees, you're increasing it by 20 degrees, right? So that we would expect approximately a quadruple in the rate. Okay, but rather than rely on this, it's best to always calculate it with empirical data anyways, right? So anytime that they're asking you to evaluate this, if there's data available for calculation, you should use the data to show that, right? In other words, it's not an answer to say doubling or increasing by 10 degrees doubles the rate. That's not really a good way to answer things. You should always use data if data is provided. If there is no data, then fine, then say that. Okay. So, at any temperature is a wide range of distribution of kinetic energies, and what you're seeing here is that at a higher temperature, the curve shifts, meaning you've now got a greater proportion of the sample that has met the activation energy. Whenever you increase the temperature, you are increasing the population that has enough kinetic energy. So if the activation energy is here, just to kind of show another curve. So here's one. Here's another. Here's another. What are you noticing about these lines that I've drawn?
There's a higher proportion of molecules that are above E sub A, so there's going to be more effective collisions.
Possibility for more effective collisions, because remember, kinetic energy is not the only factor.
Correct.
Okay, so yeah, as we increase the temperature, but also notice that regardless of how much I increase the temperature by, there's always going to be some molecules that have low kinetic energy. Right? Whenever you increase the concentration, you're still going to have some with low kinetic energy. So it's not the same shape, is my point, the curve. Okay, it's not just like literally transposing it, moving it to the right or left. Right? The shape is going to broaden and it's going to flatten as you increase temperature. Okay? Okay. So, by the way, this is what happens when I scale a test, right? Okay. Let's talk about concentration. We kind of already talked about this, but I'll mention it again. If there are more particles per unit volume, then more collisions will occur. And thus, the rate of collisions is directly proportional to the concentration. So let's be a little clear about this, right? We increase the concentration, you are increasing the number of collisions, which will increase the number of effective collisions, increasing the reaction rate. What are some ways that we can increase the concentration? Well, literally, we can add more reactant. What's another way of increasing the concentration?
I guess like you can like evaporate water from a solution.
Reduce the volume. Right, so consider a piston system. Right, if they're closer together, they're highly concentrated. Right, and the closer they are together, then the more collisions they will have with each other, then increasing the possibility of effective collisions. Okay. So that's why we say, the rate of collisions is directly proportional to the concentration. Okay. So then, now we talk about the step-by-step process of explaining chemical reactions. And this is what we call the study of reaction mechanisms. So often a reaction occurs of a series of simple one-step reactions. Each step is called an elementary process, and the sum of them is what we call the reaction mechanism. So a mechanism is a series of steps. Now, in any reaction mechanism, one of the steps is much slower than the others, and that's called the rate determining step. The slow step in any series of steps is the one that determines the overall speed of a reaction. Okay? So, a couple of rules about mechanisms. The steps must add up to the overall reaction, right? So there's algebraic addition and cancellation. The rate law from the rate determining step must be consistent with observed rate data. I'll get into that in a minute, okay? And a proposed mechanism can never be proven correct. We're going to come up with mechanisms, but you cannot prove that that's the right way. But you can disprove mechanisms if they don't mathematically equate to the data that you see. All right, so you can only disprove. All right, so for example, let's take this first reaction right here. Nitrogen monoxide reacts with oxygen to form nitrogen dioxide. Okay, and so the rate law has been determined to be rate is equal to K times NO squared times O2. Two mechanisms have been proposed. So this is a multi-step, or the two multi-step reactions have been proposed. So first, if we look at these, there are two steps in this mechanism. Do they algebraically equal the overall reaction? So here's the overall reaction. Each of these two steps are elementary steps. So what happens when I add those steps together? Well, let's see, NO3 and NO3 cancel. And I'll have 2NO plus O2. That will form 2NO2. So first and foremost, does it pass the test of equaling the reaction, the overall reaction algebraically? Yeah, it does. Okay, so it passed the first hurdle. Now, note that in these reactions, you must be told which step is the slow step. And as we just said, the slow step is the important step. So, does the rate law match the reactance of the slow step? And here's what I mean. Look at our rate law. Our rate law says the rate is equal to K times NO squared times O2. Okay, so if we look only at our slow step right here, we have NO3 reacting with NO. All right, so doesn't look like it matches it just yet. But what we just canceled out, NO3, anything that is produced but subsequently consumed is called an intermediate. So let's define it. So intermediate is produced in mechanism and consumed, hence does not appear in overall reaction. So let's stop and make sure we understand that. Anytime you see a series of steps and there is something that is made in one step, but then it is broken up in a following step, that is called an intermediate. Look at this second reaction here. You guys see how N2O2 and N2O2 is made in the first step, but it is consumed in the second step? That is also an intermediate. Okay, so let's evaluate the second reaction. Does the second reaction algebraically add up to the overall reaction? So if I take the reactants that are left, I will have 2NO plus O2, and I will form 2NO2. So yes, it does, right? So the algebraic reaction here works as well. So now let's pay attention to the slow step. So in the slow step, do the reactants of the slow step match the rate law? Well, what are my reactants of the slow step? N2O2 and O2. Look at your rate law. Your rate law is showing NO squared times O2. The square means that in your slow step, you should have a coefficient of 2 in front of NO. So this does not, because what we're looking for is an elementary step that has these as your reactants. So going back, let's go back to the first example here. We said NO was an intermediate, okay? Now, well, okay, so we'll leave that one as is. So right now, neither of these is a perfect match. So neither of these match what we're looking for. This is just going to take lots of practice. So let's just go through a bunch of these, and eventually you'll start getting quicker at this. So let's look at problem 1 here. Here I've got an overall reaction. So here I'm proposed the mechanism. Do these two steps algebraically add up to the overall reaction? Well, let's see. I've got NO3 made and NO3 consumed. So NO3 is my intermediate here. Does anything else? What else do I have here?
Is NO2 supposed to cancel out, or is it NO2CO2? Or is it supposed to be plus?
Oh no, NO2. So if we have two NO2s here, but there's one on NO2 made, then one of them cancels. And so what you're left with then is one NO2, one CO, one NO, one CO2. So yes, this does pass algebraically. Now, let's evaluate the slow step. The rate law is based on the reactants of the slow step. So my rate law will be rate is equal to K times NO2 raised to the second. And in that elementary step, the coefficient of 2 becomes the exponent. But this is only true in the elementary step. All right, let's look at the second problem. So the overall reaction is given. The observed rate law, so we have the observed rate law here. Now again, when we say observed rate law, that means determined by experimental trials. Just like you did, right? By varying concentrations, measuring the rates, determining orders. Which of the following would affect the value of the rate constant? Okay, so increase the partial pressure of hydrogen. So these are all gases. That's why they're mentioning pressures. Okay. In a rate law, so if you change, so that would be equivalent to saying changing the concentration. If you change the concentration, does that change the rate constant? No, it shouldn't. Remember your lab, how you varied the concentrations? Didn't you get a constant value for each trial that was relatively close in each trial? So no. So no. Changing concentration or pressure does not affect K. Change in temperature. When you change the temperature, did that change the rate constant? Yes. Definitely. If we use a catalyst, okay, I realized we did not define the term catalyst yet, so let's define the catalyst. When you have lots of felines around your house, sometimes you forget their names. So if you have a catalyst, you can always refer to it so that they'll come calling to you, when you call the right name. That's what a catalyst is. So a catalyst, is a species that lowers the activation energy, and the way it does that, it provides an alternate mechanism. It is not consumed in the reaction therefore not considered a reactant. So in other words, once a catalyst is used, it's spit back out and then reused over and over and over and over again. Like the catalyst at the end of the reaction is essentially the same as it was at the beginning. Right? Because of this, we don't consider it a reactant or product. So anyways, does a catalyst change the rate constant? Yes, because different mechanism is used. It changes how you write the reaction mechanism. Okay, some more practice problems. The following mechanisms have been proposed for this reaction. Which one of the following are acceptable mechanisms? Explain why. And so we're still referring to, where'd it go? We're still referring to an earlier reaction here. The two, let me rewrite it here. The 2H2 plus 2NO goes to N2 plus 2H2O. Okay, so this problem is referring to that same reaction. Okay, so the first proposal says that this happens in one step. One step with 2 molecules of hydrogen reacting with 2 molecules of nitrogen. Okay, so remember how the rate law, the observed rate law was, where would it, up here, rate equals K times NO squared times H2. Okay, so does the reactants of the proposed mechanism match up with the reactants in the rate law? Well, the reactants do, but everything has to match. The coefficients that turn into exponents has to match also. And here it is not the case, because look how the NO has a coefficient of 2. So, and hydrogen has a coefficient of 2. If this was just a one-step process, the rate law would show 2 here and 2 here. So this is not an acceptable mechanism. Also, it's also not acceptable because what this is saying is the simultaneous collision of 4 different molecules. Think about that. Simultaneous collision of 4 molecules, each with proper activation energy, each with proper orientation. Think about the odds of that if you're calculating probability. It's kind of like saying 4 people shoot pool balls from the 4 corners of a pool table, and they all hit exactly in the center of a pool table with the same speed, same time, right? That's not likely. So, okay. Let's look at mechanism 2. So mechanism 2, let's add these up. Should have left more room here. Okay, so what cancels here? I've got N, right? And N here, and N here. That cancels. This is not properly tabbed, but the O here and the O here cancels. All right, anything else? So what I'm left with then, what we're left with is H2, NO, NO, and H2. And our products are H2O and N2 and H2O. So the overall reaction would be 2H2 plus 2NO forms 2H2O plus N2. Does that pass the algebraic test? Yes, that matches. Right? This here matches the overall reaction, so that part's okay. So now let's check the slow step check. This is the slow step. So this is what we focus on. Do the reactants of the slow step match the reactants provided in the rate law? So H2 here and NO here, H2 and NO here, yes, except what? The coefficient is not right. So no, then. All right, on to mechanism 3. Does this add up? Let's see. N2O is, oh look, N2O is made and then it is canceled. What is that called? That's the intermediate. Okay. What else? H2, H2, NO, H2. Okay, so nothing else cancels. So we have 2H2 plus 2NO, and that forms N2 plus 2H2O. That passes the algebra test. Now let's look at the slow step. Do the reactants and coefficients of the slow step match the observed rate law? Yes, they do. So that is an acceptable mechanism. Now, again, just because a mechanism is acceptable does not mean that it's proven to be the right mechanism. It just means we did not refute it. It's an open possibility, but it's not proof that it is the mechanism. Okay. One more. So here we have an overall reaction, and we have a mechanism, a 4-step mechanism proposed. The observed rate law is provided. Which is the rate determining step? There's 4 elementary steps. One of them is the basis for the rate law. What you have to do is you have to find the step where the reactants in the rate law and the coefficients match the reactants in the elementary step. Is there a step that matches that, and if so, which one? Yeah, the first one. Because this must be the slow, and the other result must be fast. Fast steps don't matter. It's all about the one that is slow. How are we doing? Is this starting to make sense? You've got a series of steps. You are evaluating first its validity algebraically to see if the overall reaction even matches and cancels properly. And then you're going to evaluate the slow step and see that the reactants of the slow step match the reactants in the rate law that is observed, and that the numbers are right. Okay. So we talked about intermediates. And back to this reaction, where we found the rate law was experimentally determined to be this. Now, this is what we call a termolecular process. Ter as in 3. And since we're here, let's talk about other ones. So there's unimolecular, which means there's one molecule. There's bimolecular, which means there's 2 molecules. What I'm talking about is different types of molecules for collisions. 2 molecules, or 2 reactants, or 2 molecules, actually. And so termolecular is 3. So there's a total of 3, because this would be NO and NO and Br. Now, we just talked about the likelihood of multiple molecules colliding at the same time and how that's unlikely. So 3 molecules colliding at the same time is not likely. What that means then is this must be a multi-step mechanism. So here we have a proposed mechanism, and here we have the slow step. So if you base the rate law on the slow step, it would look like this. Does everyone see that? Rate is equal to K, and S stands for slow, right? So rate is equal to K times NOBR2 times NO. So here's the problem. NOBR2 is an intermediate. Okay? Intermediates are not allowed in the rate law, so it must be substituted for. So this substitution can only happen when the intermediate is in an equilibrium, which it is here. Does everyone see that double arrow? Equilibrium is our next unit, right? But for right now, you just need to recognize equilibrium as being a two-way arrow, or it'll literally say fast with equilibrium. Okay, which this one does right here. All right, so what is equilibrium? Equilibrium is when the forward rate and the reverse rate are equal. Oh, well, it says that right here. So that means the rate laws would be equal to each other. This represents the rate law for forward. This represents the rate law for reverse. If that's true, then we can equate the rate laws to each other. We just described what the rate law for the forward reaction would be. This is this one right here. Forward. This is what the reverse reaction rate law would be. And do you guys see right here? This right here, this is the fast step in equilibrium. The reverse reaction, in the reverse reaction, NOBR would be the reactant. So that's why the rate law for the reverse reaction is rate equals K times NOBR. Okay, so because the forward rate and the reverse rate are equal to each other, we set the two rate laws set equal to each other. And now what we're doing is we just manipulate this and we solve for what the concentration of NOBR2 would be. And so to do that, all I need to do is divide both sides by Kr. So this represents mathematically what the concentration of NOBR2 would be equivalent for. And this was the intermediate, which cannot be used because it is canceled, but we can substitute with this instead. So that's what we're going to do. We're going to take this, and we substitute it in. Okay, do you see how like the original rate law had NOBR? Well, we can't use NOBR2. We're going to use all of this instead. And when we do that, the whole Ks, Kf over Kr just becomes K. And the reason why we can do that is because neither of any of those values had been defined yet. And so since you have three Ks, what's the product of three Ks? If you don't even know what any of the Ks are yet, it doesn't matter what they are. We're just going to condense them into one K. So NO2 or NO times BR times NO, the result is NO squared times BR, BR2. All right, that was kind of a doozy. That's you. Let's back up and explain what I did here and why I did. So back up. If you see an intermediate in a rate law, you know that intermediates have to be canceled. Intermediates have to be canceled. The slow step requires these two as the reactants, but one of the reactants is an intermediate, which cannot be used. So that intermediate is going to probably be in an equilibrium with other things. So what you would do then is you would take the rate laws, the forward and reverse rate laws, right, which are equal to each other, and substitute in their values, or their variables, rearrange to solve for what the intermediate is equal to, concentration-wise, and substitute that in place of the intermediate, which cannot be used. And by doing so, that gives you a workable rate law, which will reflect the actual rate. And we do this because you cannot express an intermediate in a rate law. So it's a workaround. All right. And the last example then. Take a look at this example. Where's my overall reaction here? Oh, well, okay. We have to come up with the overall reaction. So let's add everything up. Let's see if anything cancels here. Okay, so that line was not straight enough. Okay. What do you guys think? Can I be canceling anything? Which? What can I? CCL3? Sounds like a 70s classic rock band. Okay. What else? Two CLs on the product side, two CLs on the reactant side. Okay. And that looks like it, huh? So my overall reaction is CHCl3 plus Cl2 forms HCl and CCl4. I was a band in college, and my bass player loved Creedence Clearwater Revival, CCR, and he kept trying to get us to play CCR songs when we played at, shows and stuff, and nobody else wanted to play it because he was the only one who really liked the classic rock, but it just did not match with what we were playing at all. So we never did, and I kind of feel bad about it in hindsight because he asked us so many times, but it just would have been so random to play like a Creedence Clearwater Revival song in the midst of like all this like punk. Anyways, okay, what is the rate determining step? Which one?
Step 2.
Yeah, step 2. Slow step. Write the rate law for the rate determining step. So the rate law for the rate determining step would be rate is equal to K times CHCl3 times CL. What is the overall rate law? Okay, so here's the thing, right? You guys know that the rate law cannot include intermediates, and we just showed that we canceled. Wait, no, we didn't. Oh, sorry, I take all that back. The rate law is simply rate is equal to K times CHCl3 times. Oh, wait, no, yeah, we do. Sorry. We do have a intermediate. What is the intermediate? Yeah, chlorine. All right, so chlorine has to be substituted for. So rate forward equals rate reverse. That means, and here is where we pay attention. Whenever we do this, right, you can only do this for the equilibrium step. Which one is the equilibrium step, guys? Right. Okay, so the rate of the forward reaction is going to be Kf times the concentration of the reactants in the forward reaction, which is Cl2. Okay? That's equal to Kr multiplied by Cl raised to the second, because those are the reactants for the reverse reaction in the equilibrium step. I'm going to pause right here. So far, does that make sense? Okay? All right, so what I want to do is look at your rate law. What is the variable that needs to be substituted and replaced in your rate law that you wrote?
The Cl.
All right, the chlorine. Okay, so let's make a note of that. Needs to be substituted. Okay. So what I want to do is I want to rewrite this equation to solve for Cl. Right? So Kf times Cl2 over Kr is equal to Cl squared. Right? But that is not Cl, that is Cl squared. So we want to take the square root of Kf Cl2 over Kr is equal to Cl. So, if that's what we have to substitute, new color, your rate, which is equal to K CHCl3 times. So what we're going to get here then is the Kf. This is really like Cl raised to the 0.5. Because you're taking the square root of it. That's what you're inserting for Cl minus instead. All right, that one was a little messy. And that's a good place to stop.